Cool. All right, so welcome everyone to today's Open Neuromorphic seminar. Very glad to have Dylan from Synsense, who's going to give us a hands-on session on Xylo and Rockpool. I'm assuming it's pronounced Xylo, like xylophone, right? I guess we'll find out in a minute. But just before we get started, a little bit of background on who we are. Open Neuromorphic, just a collaborative space created by other open source enthusiasts. We have a platform for code, hardware projects, just a cute little community of neuromorphic nerds who like to talk to each other and learn things. And we have a Discord server, and we host events, and I should probably turn off my Discord notifications. But yeah, so this talk will be recorded and uploaded to YouTube. And before we get started on that, I also wanted to show a couple of upcoming talks that Open Neuromorphic are hosting. So in a month, we have Andreas Wild from Intel, who's going to be talking about the Lava framework, along with some other very exciting presentations that will follow through the rest of the year. So with that being said, just a quick intro to Dylan. So he's a VP at Synsense, got his undergrad in electrical and electronic engineering and computer science, and his PhD in computational neuroscience from ETH Zurich. So spans all across the board here. He's worked at Synsense since 2018 as a co-founder. And if you're not familiar, Synsense are a startup that are doing very cool things for commercializing neuromorphic hardware. Their products are out in the wild. Their software is open source, and you can play around with it and hack it apart. So yeah, they're doing some really cool stuff in this space. So with that being said, I'd like to pass the proverbial microphone to Dylan and let you take over.
Great, thanks very much, Jason. And thanks again for the invitation. It's really nice to be able to be with you guys this evening, show you what we've been working on. One quick correction: I'm just an employee at Synsense. I'm not actually a co-founder. I wasn't quite that early. It was a month or two too late to be technically a co-founder. Yes, but I have been at Synsense since 2018. I didn't do my PhD in neuromorphic engineering, but I started out working very closely with the neuromorphic engineers in Zurich, and when they started up, when they wanted to commercialize these things with a spin-off company, I jumped at the chance. It was much more exciting than working in finance or banking, which was what I assumed I was going to be doing. Yeah, so today I'm going to give you a bit of a background of the company and of our hardware, our technology, our software stack. I'm going to do a live coding session for training and deploying an SNN to our spike-based hardware, Xylo. Xylo it's pronounced like xylophone. It's actually from the carpenter bee. The species is Xylocopa, and bees are, of course, these amazing little machines with tiny brains that can do incredible things with vanishingly small power consumption. So, of course, that's very much what we like to do. In the spirit of open source, all of the code is going to be online on GitHub. This is currently private repository, but by the time this talk is published, it will be a public repository with the script of all of the live coding stuff that I'm doing. So you can follow along there. Yeah, so Synsense, for those of you who don't know the company already, we are a hardware company. We design and sell silicon chips. We want to sell hardware. It's all for very low power compute. That means, you know, a couple of milliwatts at worst, ideally less than a milliwatt, for sensory processing. So we want to put our compute as close to the sensor as possible, for processing in edge devices. So something that would go into a smartwatch, a battery-powered consumer device, a mobile phone headset, something like that. We generally want to enable neuromorphic smart sensors. So we want to take a high bandwidth sensory stream like audio or especially vision, put a little bit of compute close to that sensor and convert that high bandwidth input stream into a very low bandwidth, very informative few bits of output. So we want to do a full vision processing classification stack, or a real-time audio classification processing pipeline, where we just output the results of the inference. So a couple of bits of whatever class the sensor is experiencing at the moment. So we look at use cases like smart wake up, continuous monitoring use cases, keyword spotting for audio, things like that. We want to be operating for human-computer interaction, which means that we aim for real-time latency, so 200 milliseconds or less real-time human interaction. And as I said, low power is where it's at for us. So that always means less than 10 milliwatts average continuous power, ideally much less than that. I neglected to mention at the beginning, if you have some questions, just jump in anytime. I think you have to write into this little Q&A section, but either Jason or Greg or Fabrizio will jump in and raise the question. I do want this to be interactive, so jump in if I gloss over something or I'm going too slowly. You can also tell me. Okay, so we do have two main classes of hardware at Synsense. One is for vision processing. So on the left, you see Dynaps CNN, which is our spiking convolutional neural network processing cores, and a processor, standalone processor, and SPEC, which is our fully integrated smart vision sensor. So this combines a DVS-style event-based vision sensor array, a low-resolution array, with spiking convolutional cores for processing on the same chip. These are asynchronous digital devices. That's obviously for vision processing. On the other family of hardware we have is Xylo. I'm going to be going in more detail on Xylo today. Gregor, I think, focused a bit more on SPEC a few weeks ago, so you can catch up with that presentation if you want to see information about the vision processing hardware. Today I'm going to be talking about audio processing and Xylo. Xylo is designed for natural signal processing, which basically means anything except vision. Temporal signals like audio, biosignals, IMU, motion, human motion, signals like this. This is a synchronous digital device. In both cases, the computational element is based on spiking neural networks. And I'm certain I don't need to introduce spiking neurons for this audience. But what I wanted to emphasize here is a couple of things. Firstly, the computational unit obviously has a lot more complexity compared with a standard ANN unit. And there's all of these T's in brackets for spiking neurons, right? We've got time as really a crucial component of the computation. We've got multiple states, temporal states inside the neuron. We've got the synaptic state, the membrane potential state. Both of these are integrating information over time. The communication between these units is in the form of spike trains. These Zi and Zo of T. So there's these key points of difference in computation, obviously, between spiking neurons and analog neurons. And the goal of our hardware, and especially the goal of our software tool chains, is to make it as simple as possible for you to use these fairly sophisticated computing elements to solve whatever use case, deploy whatever task you would like to deploy on this hardware. And hopefully I can convince you this evening that it is easy and fun. So our toolchain for Xylo is called Rockpool. You can find it at rockpool.ai. And this is an open source toolchain, obviously, or I wouldn't have the chance to speak with you this evening. It's a Python-based toolchain. We build on top of other industry standard tools such as PyTorch and JAX. And the goal is that we have a deep learning framework for spiking neurons, which takes you all the way from a very high level, simple API, where you can define the network in a convenient, familiar syntax, assists you with training, handles some of the training complexity which is of course higher for spiking neurons than for artificial neurons. And then also helps you with the quantization, the deployment, the mapping, and interfacing with the hardware itself. And so using our tool chains, you can really stay at a very high level in Python, train your network, do the deployment, interact with the dev kit, all from Python, and with a convenient API. So that's what I'll demonstrate to you this evening. So when you want to get started with Rockpool, you should visit rockpool.ai. We have a lot of documentation there, a lot of tutorials. This is the easiest way to get started with our tools. We have, ranging from very simple introductory material through to detailed documentation about each of the modules, each of the components in Rockpool. High-level tutorials about how to train fairly complicated spiking neural network architectures such as WaveSense, which is published by Cedric Sheik and Philip Vidal a year or so ago. Overviews of our hardware, so information about the Xylo architecture, or the way it's designed, the way you interact with the devices is all there on the web and the documentation. Rockpool also recently, just in the last release, provides support for training, hardware-aware training, also for mixed signal devices. So in particular for the Dynapse 2 family of chips, we have simulations in Rockpool, trainable simulations of the hardware architectures, as well as information in the documentation about those mixed signal architectures too. So there's really a lot of stuff on the web, on the website there. That's the way to get started with Rockpool. Installation. Sorry,
question on my side. So for those of us that are less familiar with JAX, what motivated having a tool chain that was compatible with JAX?
It's a little bit for completeness. When we first started building the modern version of Rockpool, JAX was a little bit up and coming, but I liked the fact that so JAX, similar to PyTorch, takes care of the hardware acceleration and compilation for you. So you can write your code in Python, and it will compile it to something which either runs in an accelerated form on your CPU, on a GPU, on a TPU, because JAX is from Google, as well as cross-platform. So if I've got a Mac sitting on my desk, JAX supports the native Mac hardware acceleration, plus it's the auto differentiation. So it gives you the auto differentiation of Torch, as well as the acceleration. At the moment, I think Torch is probably more heavily used, especially in research, than JAX, although JAX is certainly growing as a community. However, TensorFlow in industry is number one, and JAX uses the TensorFlow backend for all of its compilation and deployment. So it's a little bit hedging our bets. The nice thing about Rockpool is that the API at the high level is the same, whether you're using PyTorch or JAX, or just NumPy if you don't want any acceleration or training. Yeah, so to briefly get into that. Today, I'm going to stick with the PyTorch backend, just to kind of presage things there. Okay, so installation of Rockpool is very simple. You can install it with Conda, you can install it with pip. And again, this is also documented on the website if you want to get started. Okay, so now I'm going to switch over to live coding. And what I'll start with doing is showing you what a module looks like in Rockpool, in particular, a spiking LAF module, how you configure it, how you define it, how you interact with it. So first, just to begin with, I'm just going to copy and paste some imports here, because watching me type imports is probably kind of boring. So we'll pull in matplotlib, nice printing, Torch and NumPy, as well as ability just to show PNG files. Okay, so we need to import the LIF module from Rockpool. These are all under nn.modules. So this is our kind of neural network sublibrary for Rockpool. And we have a module called LIF, leaky integrate and fire neuron. It's designed to mimic the order of computation on Xylo on our hardware, and so it becomes easy to deploy. You can use this module to build up larger network structures, more complicated networks, and have some confidence that even though this is a floating point simulation on CPU, we can transfer this over to the hardware fairly simply. So to create a module, we say how many neurons we want, which in this case is 1, and I'll set a high threshold so we can just easily interact with it. And there we have a LIF, single LIF neuron. Now let's generate some process input for this neuron. I generate 500 time steps for 1 neuron. So we'll make an input spike train, just using NumPy random numbers. So now we have Processonian event train, and let's just plot that. Okay, so there's our few low rate Processonian input events, and now we evolve the LAF module just by passing the data into it. So I give it these input events and pass it through the module, and and we get the output. Come back to these extra output arguments in a moment. And then let's just plot the output. So there, let's do it. Okay, so there we have a few spikes on the output. So spiking input channel, spiking output channel from the LAF neuron. But of course, we'd like to see what's going on inside. And so we can pass this extra argument, record equals true when we evolve. And we get back here a dictionary of stuff going on inside the neuron. Let's take a look at what we got here. So we have the synaptic currents, membrane potential. It's actually recurrent input currents and the spikes from this module. But let's take a look at the synaptic currents. Oops. Didn't like that. Oh, of course, need to squeeze it. Okay, so there's our synaptic inputs corresponding to those Processonian input events. Let's look at the membrane potential at the same time. So now we have the synaptic currents in blue and the membrane potential in orange. We can see when we're hitting threshold here at 10, which is what we defined as the threshold, and producing these output events. So, so far, so good. So modules in Rockpool all have a common interface. You'll evolve them just by passing data to the module. They also provide a few extra interesting methods. For example, the state method, which lets you see what is the current internal state of the module. All the modules in Rockpool are stateful by default. This is obviously essential for spiking neurons. They do have an internal state which evolves over time. Here we got the time course of that state. Here we see the instantaneous state of the current state of the module. We also have, we can see the parameters of that module, which in fact are the trainable parameters. So by default, as much as trainable as possible in Rockpool. Here we see that by default, the time constants, the bias, the threshold are all trainable parameters of this LAF neuron. We can also see the non-trainable parameters, the simulation parameters. So here we've got the time step, some noise, a couple of other non-trainable parameters of the simulation itself. Okay, so that's a single LAF neuron, a single module in Rockpool. Any questions related to that before I quickly move on?
I have a question, Dylan.
Yeah, sure.
Why does it say max spikes per DT here?
That is because that's sort of a hardware-aware training feature of this neuron. On the hardware, we can only produce a limited number of events per time step and the output of a neuron. You can specify here it's obviously set to a very high value, which we're never going to reach, but you can set this to a lower value if you want to limit the number of output events per time step. This is then taken into account during the simulation of the LAF neuron and therefore also during training. And so if you have these sort of hardware constraints, then you can apply them during training and ensure that the deployment to the hardware retains accuracy. You don't lose performance.
Yeah, on the note of that max spikes per DT, I think that's a pretty nice feature to make your hardware more efficient. To clarify for the crowd, those of you, so it's not a single neuron, right? It's a full layer. How many spikes from that entire layer, right?
That's correct. No, it's how many spikes per neuron within that layer.
Over time? No, per DT.
Per time step.
So you can generate multiple spikes per time step, and does that manifest as like a, don't want to call it a graded spike, but just like an accumulation of n spikes?
Yeah. So so we have a time stepped simulation of the LAF neuron. If you at some point in time have an extremely large input, but then you'd like to cross the threshold multiple times in that time step, that gives you a more accurate simulation of the LAF dynamics that you would really like to be simulating in continuous time. So it's one of these little tweaks which improves the accuracy of the LAF simulation. And we have something similar on hardware, so that the hardware neurons can generate multiple events in a single time step. And that improves accuracy. For a similar reason, when we cross the threshold, we reset by subtracting the threshold. We don't reset by setting to 0. And it's a similar kind of, just a little bit of additional computational accuracy for the LAF simulation.
That makes perfect sense.
Okay, great. So obviously a single LAF neuron or even an array of LAF neurons is not particularly useful on its own. We'd like to be able to build up networks of these things. And so I'll show you how that works in Rockpool. Just for visualization, I'll show you what we're going to build. So we're going to build a very small, very simple 3-layer spiking neural network. Technically, it's a deep network because it's more than 1 layer. So you can tell Jan LeCun I said so. Okay, so to do that in Rockpool, we need to import the required modules. So the linear module is a set of linear weights. That's these weight blocks. And the LAF is obviously our LAF neurons. Here, the numbers are the number of elements in those layers. So I'm just going to build a 2-layer spiking neuron LAF layer here, a 3-neuron layer here, 2-layer neuron here on the output. The way we compose these modules into networks is by using combinators. So I import the sequential combinator, and now we can build up a network. So sequential is a combinator which just lets you specify a list of modules. If you're familiar with PyTorch, this will look very, very similar, very familiar to you. So let's build up this network. So we've got 2 input channels and 2 output channels from that linear module. Then we've got an LAF block with 2 neurons. Then we've got the second set of weights, which has 2 input channels and 3 output channels, followed by 3 LAF neurons. And then the final layer is 3 input channels and 2 output channels, followed by 2 LAF neurons.
We'll need you to scroll down, Dylan.
Oh, is it cut off actually?
We're good now.
Okay. All right, that's
also another quick question. Is there a difference
yes.
between linear layer defined in Rockpool versus PyTorch, or is it just a matter of, we want to know exactly what's happening in this linear layer such that it's compatible with our hardware, so we want to fix that and not be dependent on possible changes that PyTorch make?
There's minimal differences. Here I'm not using haven't specified to use the torch backend at all. This is in fact just using NumPy. So this is something which we have to code ourselves. One of the main differences is by default, there's no bias on these linear layers in Rockpool. Because generally when you're building these spiking neurons, the bias you incorporate into the LAF dynamics. You don't want to inject that just on every synapse. And so to save people from specifying as bias equals false for every single linear layer that they ever define, we change the default. So in PyTorch, the default will be true. In Rockpool, the default is false. So a couple of small things like that. Rockpool, there's other stuff going under the hood to support deployment. Rockpool modules know how to serialize themselves in a way which can be deployed to neuromorphic hardware. Obviously, PyTorch doesn't target neuromorphic hardware yet. Yeah, so there's a few little bits and pieces there, but fun. But, in terms of, in principle, it operates in the same way. Okay, so now we have this.
Sorry, there's one more question.
Yes. Oh, please go on.
Tendi. So can we use the PyTorch sequential model, or are we stuck with the Rockpool combinators?
Let's see. You can use PyTorch sequential. Rockpool torch modules can mimic torch modules and can have the same PyTorch API. So you can use the LAF module from Rockpool and use this within a PyTorch network with no issues, but you won't be able to deploy that because it will be missing all of the kind of Rockpool machinery in order to do these things. And yeah, you lose some of the additional benefits of convenience things that Rockpool gives you, which makes it easy to train spiking neural networks, which PyTorch, of course, doesn't need to give you. So maybe we can touch on that point again later, but in principle, yes, is the short answer to your question. Okay, so Net is itself a Rockpool module, which means we can interact with it exactly the same way as we did with a single LAF spiking neuron. So for example, we can look at the parameters, and now we see a nested dictionary containing all of the trainable parameters of this network, which is the weights for these linear modules. It's the time constants, the biases, thresholds, etc. for the LAF modules. One of the nice things that Rockpool can let you do is you can specify parameter families. So if I just want to see the weights, I can say, just give me the weights. If I just want to see the time constants, I can say, just give me the taus, and things like that. So because there's these different classes of parameters in a deep spiking network, which you don't have to deal with for a standard ANN, there's these extra convenience things that Rockpool tries to do for you. Similarly, we can look at the state of this entire network. Obviously, the linear blocks don't have any state, but the LF blocks do. So again, we get the nested state of this entire network. Yeah, there's another question.
Yes, from me. So basically, I see that all the weights and parameters here are expressed in floating point. Does Rockpool perform the quantization we're training, matching the Xylo hardware by default, or does someone need, or you perform quantization after training when deploying to the chip?
By default, so the LAF module is a floating point module. We do have a quantization aware training pipeline in Rockpool, which allows you to use that same LAF module and apply quantization on the fly to it during training, which you can then match whatever bit depth or whatever hardware constraints you have. So that's kind of broadly our hardware aware training pipeline. We also offer some post-training quantization utilities specifically for Xylo, which I'll show you towards the end of the coding session. But by default, everything's floating point. Okay, so let me flip back quickly to PowerPoint here. So that's the first introduction to Rockpool and what these modules and networks look like. Now let's build that up and train an actual use case. So what we're going to do today is train a network to solve the spiking Heidelberg digits use case. This is from the lab of Friedem and Zenke, who's actually just across the river from me. I'm in Basel right now. He's across the other side of the Rhine. This is if you're not familiar with it, it's a neuromorphic data set. It's an audio data set containing spoken digits, 0 to 9 in both English and German. They recorded from a whole bunch of people speaking these digits, and then they pre-process the audio with a very sophisticated basilar membrane cochlear model to convert to events. So what we have actually is an event data set with a very fine temporal and frequency resolution of the data in a bunch of event channels. And this is what we're going to classify. So we'll classify actually the first 8 classes of this FHD data set. There are references here on the slides. The slides will also be in this GitHub repository. I don't know if you post them on the Open Neuromorphic website or not, but in any case, I'll make them available. You can check this out, and you can check out the information about this data set with the paper reference down here. For accessing this data set, we'll use another open source toolchain called Tonic, which you're probably also familiar with. Gregor is one of the main developers of Tonic. Synsense has sort of adopted Tonic to some extent. This is what we use also for our data set wrangling. It provides a lot of very useful tools. It provides access in a very simple way to a whole bunch of neuromorphic data sets, including spiking Heidelberg digits, spiking MNIST, the IBM DVS gesture dataset, many others. It has a bunch of neuromorphic tailored data transformations and augmentations that you can make use of. It works very conveniently with the PyTorch dataset data loader pipeline. So it's a very convenient way to play with the neuromorphic data sets. Provides caching for you, both disk and memory caching, which speeds up training a lot.
I've got to mention,
and of course, it's open source.
One of my students was doing a bunch of data loading. We're trying to figure out why it took like a whole day for an epoch. Hit the disk cached data loader, bam, 500x speed up. Very happy.
Yeah. It's really crucial. There's also a memory cached data set. If you can make sure your entire data set fits into your GPU memory, then it's probably 1,000 times over just loading each sample. So absolutely, Tonic is fantastic. So okay, let me switch back to the code session here. Okay, so we're going to use Tonic. I'm going to import Tonic here. I'm going to use Tonic to get a training data set. So we just say Tonic datasets SHD, and we tell it where to put it. So Tonic will download the data for you, unpack it, wrap it up in a nice Python-based interface, and give it back to you as a Python object. So that's very convenient. I'm just going to write down a few other things here about the data set. So the time step of the data, the number of input channels that the data has natively, and the number of classes it has natively. Okay, so I'd already downloaded the data, of course, beforehand to save us doing that. So that was very quick. Now let's pull one sample and have a look at what we have here. So I can just say train data, get one sample. And now events is a NumPy array. We need to get the time stamps from that. And we need to get the corresponding channels from that. And then we can plot this. Okay, so there we go. There's one data sample, a bit under a second long, 700 channels of high resolution spiking event data. For the purposes of this evening, we're going to downsample that. That will speed up training, makes the network a lot simpler, And also the Xylo hardware only supports a limited number of input and output channels. In particular, it supports 16 spiking input channels and 8 spiking output channels. So what we're going to do is downsample these high resolution data samples to 16 channels, and we'll downsample the time step as well to speed up training. So we'll specify we want 16 channels and time step of 10 milliseconds, and the maximum duration of 250 time points. And we will use the tonic transformation tool chains in order to do this downsampling for us. Tonic provides a transforms library, and we can build up a transformation, a composer transformation pipeline using this compose constructor. And we use a downsample transformation provided by Tonic. So give it a time factor, SHD time step divided by net dt for the time downsampling, and some spatial downsampling as well, which is the net channels divided by SHD channels. And then on the back of that, we want to rasterize. So we use another transform from Tonic called toFrame. So we're going to rasterize these, each of these samples. I'm not going to go into great detail about the syntax here. Then we want to convert each of these samples to a torch tensor. And I'm going to trim them in time. So I'm going to just add another lambda function here.
This might be one for Gregor, but does the spatial factor, when you're downsampling channels, does it just drop channels or does it accumulate them?
It literally just divides, it multiplies all the X and Y's by that factor. So you, it doesn't accumulate, it just, yeah, drops them basically.
Gotcha.
Well, no, sorry, no. Okay, I see what you mean. No, the number of events stays the same, so it accumulates it. Yeah,
they'll end up being compressed into
yes, exactly.
Into the channels. Yeah,
you have multiple
okay.
spikes at the same time. Does that sum to a 5 or something?
No, this is event. So this is basically, if you think about the list of X, like X's as all for all events, then you just divide all these X's by that, or multiply it by that factor. So you will end up with the same amount of events, but just yeah, compressed. If you have the image, I think it's easy to think about if for an image, then you will squish all the events into a smaller on like spatial size.
Mm-hmm. Gotcha.
We can also take a look at this. So here what I'm doing is recreating the data set and providing this transformation pipeline. So every event now that comes out of the data set will go through this transformation pipeline. So if I get one of these rasters from this training data set, then we can see raster is a torch tensor. You can have a look at it actually, and you should be able to see the accumulations. Yeah, so there you go. So now we've got 16 channels and 90 something samples in time, and you can see that it's accumulated the events over time and over channels. Yeah, okay, and this is what will pass into the network. Okay, so now I'm just going to copy and paste. We need to subset the target classes. So spiking Heidelberg digits gives you 20 target classes. We only want to use the first 8. So I'm not going to go into great detail with this, but what I've just created a little data set class which picks some range of labels and only returns samples that match those set of labels. So I'm then going to create a data loader, which is a torch data loader. So torch utils data loader, using the disk cache data set here, using this subsetting class that I just wrote for the first eight output classes. And this is the tonic disk cage data set. And we're using the same training SHD data set that we had before. So now I have just a standard torch data loader, and this is what we're going to use for training our network. So speaking of networks, let's have a quick look at the network that we will train. As I said before, we have only 16 input channels on Xylo and 8 output channels. And so the network that we will define is going to match that, that architecture. So we've already downsampled the data to 16 input channels, and we will specify a spiking network with 8 output channels. And this is the architecture I'm going to use here. So I've deliberately chosen, it's a small network. There's only 20 neurons in each of these layers. We've got 2 hidden layers, but it's also a bit sophisticated, right? We're using a residual block here, which means we've got these skip connections around this intermediate block. This is kind of just to show off that we can simply define these, train these, and deploy these in Rockpool. I'm not sure it really provides a lot of accuracy benefit for this particular use case, but for advanced deep neural network architectures, things like residual blocks, skip connections are all show important benefits. So here I'm just showing off. I hope you forgive me for that. So now we need to import the modules that we need. So from Rockpool modules, we'll get the torch. So LAF torch is an LAF module with a torch, using a torch computational backend. We have a bunch of standard modules in Rockpool. LAF is one of these. It's guaranteed to be exactly the same computation, whether you're using the torch backend, NumPy backend, JAX backend. That's a standard module. So in this case, we're using torch. We're also using the torch-backed linear weights module. And again, we need the combinators. We're going to use sequential. And we have a residual combinator also in Rockpool, which helps us define this residual block. So number of input channels is going to be this 16 channels that we defined before. Number of hidden neurons is going to be 20. Number of output neurons is going to be 8. And then we can build up our network architecture, very similar to as how we did before. LAF layers.
So this is super exciting because I didn't actually realize you could use residual connections in the PyTorch sequential constructor. Maybe I'm wrong, but yeah, it seems like you've advanced the hell out of that.
Well, I confess I don't know how you do that exactly in PyTorch and whether that would work in exactly the same way. Maybe someone can jump into the chat and verify that. But yeah, well, we can anyway.
In your face. No, this is great.
Your face, PyTorch. No, we love PyTorch. Without PyTorch, life would be a lot harder.
Yeah.
Okay, so now we've got the output layer.
Is there a limit on the number of layers like in spec, or it's just a matter of limitations in parameters that can be stored on Xylo?
That's a good question. There's no limit. There's no explicit limitation on number of layers, but you have, depending on what hardware you have a limited number of neurons. And so if you have 1 neuron per layer, you can go up to 1,000 layers, but that's probably not what you want. So that, yeah, you've got resource constraints on the hardware, obviously, but there's no, when you're training things in simulation, there's no built-in limits on any of these things. You can go as deep as you like.
Yeah, I meant on the chip. And more or less, how many neurons or synapses is able to store Xylo on chip?
There's 1,000 neurons with up to, so on average, 32 input synapses. So 32, and there's actually 2 synaptic states on this particular chip. So that would be 64K synapses in total, and 1,000 spiking neurons. I'll show a diagram of the Xylo architecture itself as well.
Okay.
In a few minutes. So
okay.
Also discuss in more detail there. Okay, so now I've defined this network. We have a sequential module. We can again see the kind of nested structure of this network. We can see this residual block in here with its linear and LAF layers. And again, you know, all of the, this is just a Rockpool module. We can look at all the parameters. And as I mentioned before, by default, everything is trainable. So of course we have these trainable weight blocks, but then for the LAF layers, we also have the membrane potentials, the synaptic, the membrane time constants, the synaptic time constants, the biases, thresholds, etc. For those of you who have trained spiky neural networks, you will realize that this makes life a lot more difficult to train, right? It's a lot harder to train time constants and thresholds than it is to train linear weights. And so for the purposes of this demonstration, I'm going to not want to train those parameters. I want to fix them and make them non-trainable. So Rockpool provides an easy way for you to do that. Rockpool parameters, there's a decorator called constant, which specifies that this particular parameter should not be trainable, should be obviously a constant value. So what I'll do is I'll define a dictionary of the neuron parameters, which I can then assign to each of the layers. And what we'll say is we'll specify each of these parameters to be constants. So we'll say 50 milliseconds for the synaptic time constants. Let's say, let's do it the other way around, 20 milliseconds for the synaptic time constants, 50 milliseconds for the membrane time constants. Let's fix the biases to 0, and we'll also fix the thresholds to 1. And we need to specify what the time step is for the simulation of these neurons. So we've specified that before, as we had for, that was 10 milliseconds. So now I can redefine this network. Why don't I just copy and paste it so you don't have to watch me typing that out again. And now I'll just pass these neuron parameters in to each of the LAF neurons. And when I do that, I'll again get the same network. And if we look at the parameters now, we will see that there's only the weights for these linear layers, but the LAF layers no longer have these additional trainable parameters. So Rockpool provides a lot of facilities like this to help you manipulate the parameters, what you want to be trainable, whether you want to train them per neuron on a per neuron basis or a single value per layer, things like this. All of these things are possible.
Yeah, so
okay.
I had to look it up. So PyTorch by default doesn't enable residual connections and sequential constructors. You have to create a separate class. So man, that res block is genius, and it needs to be ported to PyTorch's default implementation.
That's interesting, because the residual block itself is very simple computationally.
It is, yeah. I guess that they're just trying to encourage use of like a class that inherits from an n-dot module or something rather than sequential.
I see.
Still super
well,
clean.
You know, if you're impressed by that, the more impressive thing to me is that you can just deploy it to the hardware, right? So I can build a network with this residual block, and it knows how to deploy itself to neuromorphic hardware.
It's beautiful.
Okay. All right, but first we got to train this beast. So we do that just with the standard Torch training tools. So we use Torch optimizers. Let's use Atom, fairly standard these days. We'll use a cross entropy loss from Torch. We initialize, initialize Atom optimizer. This as Torch method converts from Rockpool parameter dictionary to a Torch parameter generator. And then let's specify loss function is just cross entropy loss. Okay, and now we just have to build up a training loop, a Torch training loop. Let's just train for 10 epochs. Oops, for E in range epochs. Now, in each epoch, we need to get a batch of events from the data loader. This data loader is set up to give us, I think it's 128 samples in a single batch. So we're even though the data set is coming out in single samples, the batching is all done by Torch and by Tonic, and we can train a full batch in Rockpool without, you don't need to change anything or pre-specify anything to do that. If you pass in a batch of data, it trains on a batch of data. So obviously that's much more computationally efficient during training. So we get our batch here. We have to zero the gradients for the optimizer. So this is all going to look very familiar if you've used Torch to train anything before. So we've got our batch of data. We pass this through the network. We build up a prediction on the output, which is essentially just going to be the number of spikes on the output channels. So where the target will be, we want to have the target channel should have the most number of spikes. Output. So we want to sum that over time. We compute the loss. And we do the backward step. So the magic of Torch computes all the gradients for us and do the optimizer step. And that's it. Let's print some output here. Epoch of non-epochs and print the loss. Okay. So if I run this, it will fairly slowly go through the epochs and train this spiking neural network. So this is obviously the simplest possible training loop that you can specify. There's no extra bells and whistles here. There's no regularization on any of the parameters or on the neuron states. There's no constraints on any of the parameters. You know, I'm not measuring validation accuracy or anything like that as we go through. This is a very bare bones training network. And I'm also not using any drastic acceleration. So we have a bunch of highly accelerated CUDA-backed modules for LAF training, which are much faster. So if you're actually training a deep spiking neural network, you can get this, and you're running on a big fat GPU. This will be, instead of 5 seconds on my poor little Mac Studio, it'll be running at multiple epochs per second, much faster. Okay, so I'm just going to, here's one we prepared earlier. I'm going to load a pre-trained set of weights that's been trained for 37,000 epochs instead of just 10, because the performance will be much better. Whoops, didn't like that. 37 killer epochs, there we go. Okay, so now net is my Rockpool module. I've used save previously to save the parameters, and I can just use load, and I have this JSON file, and I get all of the pre-trained parameters into my network. I did save an image of what the training process looks like for that set of weights. So I'll just plot that there. So here we have the training process over epochs on the x-axis. In blue is the cross entropy loss, and in orange is the accuracy over epochs. So we get up to about 97% training accuracy on these A classes, and about, if I recall correctly, it's something like 73% test accuracy. If you're interested. Okay, so let's see what we got out of this train network. Let's get a single training sample, and we'll pass this through our network again just by passing in the data. And let's record the internal state just so we've got it. And now let's plot this. So let's look at the output channels. Okay, so there's the output events. I'm going to clean this up slightly. 0 to 1 second. The Y channels are minus 1 to 8. So you can see all of the output channels. There we go. So on X is the time axis, on Y is the output channels, and we have most events coming out on this channel number 5. Let's plot, just for sanity, what was the label here? Label, yeah, what was the label? Okay, so now we see that it was in fact label 5, and indeed that was where we put out the largest number of events. So in this case, we've correctly classified this input training sample. Fabrizio has a question.
Oh, yes, there is a question from the audience. Hello, Dylan. How can I use Rockpool to train a network online for a reinforcement learning task?
That's an interesting question. You would have to build up or use some standard reinforcement learning task definition and loss definition and training loop and choice of optimizers and so on, and then you can slot in your model, right? So we've actually never done this. I've never done reinforcement training of a spiking neural network, but because we're using all of the same Torch backends, then you can have a training framework in PyTorch for reinforcement learning, and you just swap out the model, and PyTorch will do all of the backward pass gradient calculations, etc., for you, and away you go. If that was indeed your question, another similar question might be if you want to do spike-based synaptic learning or STDP style. This Rockpool is not really designed to do. We do have some older modules which include spike-based learning rules. Maybe we can discuss this offline, or you can take a look at the documentation. These days, we're mostly targeting gradient-based training of spiking neural networks for the reason that it gives us better performance, better task performance for smaller networks. Okay, let me quickly switch back to my slide deck here. Okay, so I promised to show what is the Xylo architecture. This is where we're going to deploy our spiking neural network. What you see here is the logical architecture of the Xylo chip. This is our chip here. You can see we've got this little bee logo because it's named after a carpenter bee. We've got our 16 spiking input channels. We've got our 8 spiking output neurons with 8 spiking output channels. And in the middle, we've got a population of 1,000 spiking LAF hidden neurons. In conjunction with these neurons, we've got these big blocks of weights, 3 blocks of weights only, a chunk of input weights, connecting the input channels to this hidden layer, a chunk of recurrent weights connecting the hidden layer neurons to themselves, and a chunk of output weights connecting this hidden population to this output population. And so whatever network architecture we define in Rockpool, we need to map it onto this logical architecture for Xylo. This is where we need to do the deployment. We need to, just to step one step further in detail for the Rockpool, for the Xylo architecture. This is the digital LAF neuron on Xylo. It's an integer logic neuron. We have 8-bit synaptic weights, 16-bit synaptic state and membrane state variables. These are little digital counters. Alongside these synaptic states, we have an integer logic simulation of exponential decay, where you can specify the decay parameters for each individual synapse and each individual neuron. So this is approximating the exponential decay that you have in a simulated LAF neuron. We have bias parameters, threshold parameters for each neuron. So this is the digital neuron on Xylo. Some of our Xylo hardware, in fact, has 2 synaptic states per neuron. The one on my desk actually does. So there you have 2 synaptic decay constants and separate synaptic states per neuron. You can receive a large number of inputs to each of these synaptic states, up to 64. On average, you can have 32, maximum 32. So there's some chunks of memory on the Xylo chip where you can use up to those resources. And so there's resources for the synaptic weights. Once you fill that memory block, then that's as many synapses as you can have. So that, to answer Fabrizio's question again about the resource constraints. Okay, so just to refresh your memory, this is the network architecture that we just trained, and this is what we want to deploy on Xylo. And so what we have to do is we have to solve a mapping problem. We have to work out where in the Xylo architecture do we put these weights. So Rockpool takes care of all of this for you. This is the analytical output that you would expect for this particular problem, where you've got the input weights going, the first layer of weights in this orange block going into this chunk of input weight RAM. We've got this recurrent weight block where the second layer of weights goes in there. We've got the output weights block where the third layer of weights goes in here. And we need to work out, where in configuration memory do we put each of the parameters for all of the neurons. So Rockpool will take your arbitrary network architecture you define in Rockpool and will map it into this architecture for you, tailored for Xylo. And that can include recurrent LAF blocks, many more layers. They just get packed into this recurrent weights block. So it really solves the mapping aspect of the problem for you. You don't need to manually define where do these neurons go? Where does this configuration get put on Xylo? Okay, so let me show you how this looks in Rockpool. Okay, so the first step is that every Rockpool module, including the network modules, knows how to serialize itself. So we have this as graph method, which converts this network into a computational graph. It's kind of an opaque object. It's not designed for a user to go through and see what's happening here. But under the hood, what's happening is that this entire network is serialized with the information channels and each of the neurons with each of the parameters for each neuron, where all the synaptic weights go and all of the weights for each connection, all that sort of stuff, serialized in an object which is easy to manipulate. And so we transform this object in order to solve the mapping problem. But the user interface, we have a sub-package of Rockpool called devices, which handles all of the hardware interaction and deployment. For Xylo, obviously it's Xylo. I need to specify which chip I have. Obviously, each different chips have different constraints. So I'm importing this particular module because I know it matches what's sitting on my desk at the moment. But what we get is a function called mapper, which just takes the graph description of the network and gives me back a specification for the Xylo hardware. And so this contains a lot of stuff. Let's just look at the keys here. It contains the input weights, the output weights, the recurrent weights, all of the neuron parameters, as well as other things required to configure the hardware that match this network in Rockpool. Let's take a quick look at what we got here when we solved this mapping problem. I'm just going to plot the weights here. So let me show spec. Let's look at the input weights, and we'll look at the recurrent weights. And we'll look at the output weights.
So while we plot up, Giannis is asking, so when you mention recurrent connections in the hidden layer, does it also include lateral connections between different neurons in the same layer, or just from the neuron to itself?
It includes lateral connections between neurons within that layer. So it's a full recurrent weight matrix within each layer.
Okay, thanks.
And that would go within this recurrent weights that would go on the diagonal. So we'd have these blocks of weights along the diagonal. In this case, for this network, we haven't got any recurrent weights. And so these are 0. But here we have our input recurrent and output weights. Sorry, Jason, go on.
Oh no, I was just going to say that's optimal, because I've noticed that one-to-one connections where that neuron's only lateral or recurrent to itself, I haven't seen any practical benefit in any task that I've ever tried with just that one-to-one connection. So that's good.
Mm-hmm. The only time I would see that being particularly useful would be if you use it to simulate an adaptive LAF neuron. in which you'd have an inhibitory self-feedback. We do have a module in Rockpool that has that adaptive self-feedback, and that is in fact also deployable to Xylo. So you can train and run a Rockpool network that has ALIF neurons, and you can deploy this to Xylo by using this extra synaptic state. Okay, so just to jog your memory here, this is what we expected in terms of the configuration of these weight blocks, and this is what we got. So these 3 chunks of weights for Xylo, we put we extracted the weights out of our trained network and we put them in the correct locations. But of course, as someone, I think Fabrizio was mentioning earlier, there's a quantization step that we need to take as well. Xylo is an integer architecture. So Rockpool provides some tools for this to help you. Rockpool.transform quantize methods is a little mini library of quantization methods. So I have a function here called channel quantize, which does per channel quantization. And then I can operate directly on this specification that I got out of the mapper. Let's call this channel quantizer with a specification, and that will perform the quantization for us. And then we need to get a hardware bit stream that we can use to configure the hardware. So to do that, I call another function from the Xylo package called config from specification, and I give it this quantized specification. And if we take a look at what we get out of this configuration bit stream, we can see it's not designed to be really user-facing, but we can see that all of these parameters are now quantized 16-bit and 8-bit integers. Okay, so now we've got actually our hardware configuration. Config is a bit stream that we can use to configure the hardware. We also have in Rockpool a bit accurate simulation of the hardware, which I'll show you first. So this is under Xylo, there's a module called Xylo Sim, which I can create from this hardware configuration. And I have to tell it what its time step is. And what we get back is, again, just a Rockpool module, which we can interact in exactly the same way. But this is now a bit accurate simulation of the Xylo hardware. So let's pass some data through this and see what we get here. We get a data sample, and let's pass data through. And then we can plot the output here. This is the same sample that we used before. What did I mistype? This needs to be a NumPy array. And we want to record what's going on. Okay, so now we've passed data through. Let me fix up the limits here. Okay, so now we have time, we have channels, and this is our same sample from before, which was label 5, and we can see we get the most number of events out on the channel number 5. There's obviously some loss of precision going from floating point to a quantized, digital spiking neuron, integer spiking neuron, which you can see by the fact that the output events here are slightly different from what they were for the floating point version. But nevertheless, the performance in terms of classification performance is we're still getting the correct answer here. So now I recorded the output here. So let me just plot what the output membrane potential looks like for these neurons. Here, Sim, okay.
Are there any tasks that in which you've seen that it was necessary to perform quantization aware training instead of performing just even if these are really small networks, if you just quantize after?
Yes. So generally, quantization aware training gives you higher accuracy, high performance, less loss of accuracy when you go through this quantization step. It depends on the difficulty of the task. This is a pretty easy task. It's not as easy as MNIST, but it's not a very hard, challenging task. As your task gets harder, of course, this becomes more and more crucial. Generally, though, we've found empirically, because we've got 8-bit weights and 16-bit parameters, you don't lose a lot of accuracy in quantizing to 8 bits. We had to really push it down to 4 bits and below. Then you really start seeing the advantages of quantization aware training. But for 8-bit problems and 8-bit architectures, then post-training quantization is usually not too bad, actually. But yeah, it's not state of the art. Okay, so now we have a hardware configuration. Let's actually put it on some hardware. So I have a little dev kit here, which I hope you can kind of see if it doesn't go fuzzy. This is a Xylo dev kit, USB bus powered device that has a little Xylo chip on it with an audio interface. Here I'm just using the spiky neural network block on the chip. And I'm going to deploy this same network onto the hardware and run this for inference. So to do that, I need a helper function to find the dev kit. Oops. And let's see if it can find the connected dev kit. Okay, great. So it's identified the dev kit. This helper function will also import the correct module for you. So it's just a bit of a convenience. So you don't have to use a magnifying glass and work out what is the chip, the device ID. It will import the correct Rockpool module for you. Okay, but so we have one dev kit attached, and now I want to create a Rockpool module that that connects to that dev kit. So I need to give it the dev kit ID and the configuration, as well as the time step. And again, what I get back is just a Rockpool module, but this is now wrapping the hardware. So if I pass data into this module, it will be sent to the chip, inference will run on the chip, and then the results will be returned. And in setting this up, I provided it with the trained hardware configuration. So it's used this bitstream to configure the chip and return just a Python object, which I can use to interact with it. So again, let's pass data through this thing, mod HDK, give it the events as before, the same sample that we've been using. I need to make sure that it's integer values to send to Rockpool. I want to record the internal state. And then let's plot the output again. So now we can see, again, the same pattern of events that we had previously in the simulation. Now we have it on hardware. Let me just copy in these fix-ups to the access limits so you can see it really is the same pattern of events. Most events on channel 5. And now just for completeness, to prove to you that it really is a bit accurate simulation, I'll plot the membrane potentials of the output layer between the hardware, the dev kit, and the simulation version. And that didn't work. What's it complaining about here? Yeah, I need a time base. space doesn't work as well. Okay, here we go. So on the left, we have the membrane potential from the dev kit, recorded from the dev kit. And on the right, we have the membrane potential recorded from the simulation of the dev kit. So you can see it really is a perfect bit accurate simulation of the hardware, which lets you test deployment in a convenient way if you don't happen to have the hardware on your desk. But if you do have the hardware on your desk, the one thing that you can do on the hardware is you can actually record the real-time power consumption of the chip running with your deployed application while it's running inference. In order to record that power, here we have this other additional parameter when we evolve the module to say we want to record the power. And then let's print the output of this. Okay, so it's essentially sampled over time. I could run the main, but here you get the point. We've got something like in the order of 250 microwatts of I/O power, and that's for this this network running in inference with this use case. Of course, it's dependent on the use case. So you can really benchmark the real-time power consumption of whatever use case you deploy to this hardware. Yeah, okay, so that's the end of the hands-on section. If there are any questions before I wrap up, I don't see any in the Q&A. Okay, just jump in if there are any. I'm just going to flip back to my last slide here. So there's this is obviously a very quick introduction. Maybe not so quick, but at least it's a high-level introduction. Going down to deploying something on the hardware, but glossing over a lot of the additional stuff which you can do in Rockpool that you might need to do to get really high performance for a spiking neural network application. We already discussed the fact that there's both PyTorch and JAX backends. If you, for some reason, you want to train, if you're more familiar with JAX than PyTorch, I mentioned already that there's significant acceleration backends available. So we use one called Exodus, which is also a recent manuscript and soon to be publication, also from people, engineers in our team, which is a CUDA highly optimized LIF neuron, which speeds up training like crazy. I've got some benchmarks published for simulation and training on the Rockpool website. You can check those out. But the Exodus backend kind of just blows everything else away. It's so much faster. So if you want to be training a spiking neural network, that's what you want to be using. But if you, by chance, you have a TPU, or if you want to use the Mac hardware acceleration with JAX, this is also possible. PyTorch has some beta acceleration for the Mac's metal shaders. We have a bunch of tools I mentioned briefly for constrained optimization. This is something which is really crucial if you want to train time constants, if you want to train thresholds. You don't want to have a negative threshold. You can't have a negative time constant. You have to worry about these things in spiking for training spiking neural networks, where you don't have to worry about these things when training standard deep neural networks. Also, when training recurrent blocks, the dynamics of the block itself become crucial. This is not the case, not as severe for standard deep neural networks, even recurrent deep neural networks. So Rockpool provides you some tools to help you out with these things. We do, by default, provide time constant and threshold training. I mentioned the adaptive lift models. I meant that we've got a pipeline for quantization, hardware-aware training. I mentioned already a little bit the hardware-aware for the mixed signal blocks. We've got a fairly nice trainable PyTorch, JAX-backed simulation of the mixed signal dynapse neuron. So it's as a trainable block, you can really train with the mixed signal neuron model in the loop. And it's extensible because we need it to be. This is what we use for our development. When we have new hardware coming out, we need to be able to support that easily. So you can extend this to new neuron models, to new hardware, if that's appealing. If you have some other custom hardware which you would like to support, using this deployment and mapping tool chain that we have in Rockpool, it's very easy to extend this to another type of hardware. And of course, it's all open source. So this is something which we want to provide back to the community. We are all almost, I think almost all of us, if not all of us, from the academic community. A lot of us have PhDs in neuromorphic engineering. We really want to give back to the neuromorphic community and make your lives easier as well. So Rockpool and all of our tool chains, all our Python tool chains are open source for that reason. Yeah, so thank you very much for giving me the chance to present this to you this evening. I hope that was useful. I hope it was engaging. If you have some more questions, I'm happy to address them.
That was fantastic. Thanks so much, Dylan. If there was a clap emoji react, then we would be showering you in it.
Yeah, we're missing those. I don't know, we had this in the past.
No, that was fantastic.
I'm missing out. I'm missing out. All right, well, yeah.
Gonna have to clap IRL. No, that was, yeah, really insightful. Yeah, so if you have any questions, just pump them in the Q&A. Yeah, I guess the one question that I had was on the algorithmic side of things. You mentioned that you had a couple of different Xylo chips, maybe internal use. Did you, and some had stateful synapses. Did you find any use case or any instances where the stateful synapses helped your task?
We do have multiple Xylo devices now. The only one that's really available is this audio device at the moment. What we have on all, we have stateful synapses on all of them, but some of them have multiple synaptic states. That's the main difference there. That can be very useful because then you can support this adaptive LAF neuron. So you use one of these synaptic states actually as an inhibitory recurrent self-feedback state. And this becomes then mathematically equivalent to an adaptation variable for the ALIF neurons. So that is available on one of our devices. Yes, it's generally useful to have this memory for temporal tasks. Where we use it explicitly, there's this very nice wave sense network architecture, which I mentioned early on, which I haven't gone into any detail, but basically when you integrate the synaptic, you have the synaptic integration followed by the membrane integration, what you get is an alpha function on the membrane state. And this lets you effectively set up something like a delay. So you can configure the synaptic and membrane time constants to stimulate a delay. And this is what this wave sense architecture does. It uses those in a particular defined relationship to set up a set of cascading delays through the network. So that's one case where we've kind of explicitly used that ability. Generally, we do see that additional network parameters, trainable network parameters, gives you increased network capacity. So for a fixed number of neurons, you can get better performance with more trainable parameters. So being able to train the synaptic time constants gives you that additional capacity. We don't have a direct head-to-head comparison of where we kind of switch off the synaptic integration and just make it instantaneous and just use membrane integration. So I don't have a head-to-head comparison there, but intuitively we should get better capacity with the synaptic state as well. But it's going to be more clear on on tasks that require temporal integration.
Yeah, no, I understand. Yeah, so one, I wouldn't say concern, but just something that I'd always had on my mind was that, yeah, because you've kind of got the same exponential relaxation dynamics in your synaptic state as you do with the membrane potential, then I'd always wonder, are we just doubling up and kind of have two things learning the same dynamic, and then therefore maybe that resource would be better allocated to somewhere else. But on the other hand, you can't get that smoothing out of membrane potential, right? And that, if you were to do something like time-based learning from back in the 2002 days, where you were taking the derivative of the spike time with respect to your membrane potential. But then is that function differentiable? Otherwise, you've got a discontinuous jump, and then So
the downside of if you just have a membrane state is that you can only ever spike on the output when you receive an input spike. So you can you can't ever delay that output decision, and that's potentially beneficial to be able to do that.
Gotcha.
Yeah, in the last slide, I also saw that you cited the mixed signal hardware. Among the chips that you showed, there were only digital ones, right?
That's
the
correct.
ones at the
That's
beginning.
correct. Yeah.
Are there any mixed signal chips incoming from Synsense on this side at this point?
That's a bit of a sad story at the moment. We did want to, so that this Dynapse 2 chip, it was a collaboration between ourselves and University of Zurich, Giacomo and Divry's group at University of Zurich. And we did want to make available a dev kit, including this mixed signal chip. There were some issues with the tape out and shipping and packaging of these devices. So the hardware, the chips exist, the dev kit exists, but in practice, it's not possible for anybody to get one. So that's a bit of a shame. So we built a lot of software infrastructure to support training and deployment, in fact, for this architecture. And I still hope that at some point in the future, that this dev kit is available for people, as particularly in the research community. There's a lot of interest there. All the tools are there in Rockpool for simulation, but unfortunately, I can't sell you a dev kit.
Are we allowed to know if it's using SRAM macros for the in-memory compute, or is that a super secret source?
For Dynapse 2, it's not in-memory compute per se. It's not a crossbar architecture. It's actually a hierarchical routing, digital routing architecture. So you have mixed signal synapses and mixed signal membranes, and so you have like an analog synaptic weight per synapse, and you can route events into that synapse. So that there is actually a lot of information about the architecture on the website there. You can take a look, but it's not a crossbar architecture, and so it's neither SRAM crossbar nor analog crossbar. It's none of the above.
Any other questions? Otherwise, we can call it an evening, morning, midnight.
Well, yeah, thanks again. If some other questions arise, or anybody watching offline, just send me an email. I'm happy to engage and answer any questions there. Like I said, I'll put the slides and the coding script on GitHub. The link is at the beginning of this slide deck. And yeah, so with this kind of Q&A format, we don't get to kind of interact directly with the audience, but it was a pleasure to have you here, and I appreciate it. And nice to meet you for those who I didn't meet yet, and nice to see the friendly faces for those who I've met already.
Awesome. All right. Well, yeah, have a good one, and we'll catch you at the next Open Neuromorphic seminar, webinar, whatever you want to call it.
Thank you, Dylan.
Thank you.
Thanks, everyone. Bye.
Have a nice evening. Bye-bye.
Bye-bye.